Imagine this. Before an electric vehicle battery ever rolls onto a highway, it is pushed through brutal conditions. Extremes of heat, vibration, electrical stress, and mechanical abuse. Far beyond what any real-world scenario would demand. Why? Because safety isn't optional, it's engineered. Welcome to the world of battery safety testing, where every module, every cell, every millimeter of interconnect is pushed to the limits to ensure that you, the driver, are protected from failure. Let's go ahead and start our journey together now. Standards for EV battery testing include UL 2580, SAE J2464, UN 38.3, GTR 20, ISO 12405-3, and ECE R100. These standards form the backbone of what we call qualified safety assurance. Let's step into the lab. First up, thermal endurance. Batteries aren't just sitting idle. They live through cold starts in Alaska and scorching heat in places like Death Valley. We run batteries through cold and high temperature extremes with rapid transition rates between temperature set points and programmable environmental chambers. These are multi-day thermal shock cycles with soak periods designed to simulate seasonal extremes and sudden weather swings, along with scenarios such as leaving a warm garage and driving into frigid cold outdoor weather. Key metrics we look at for battery safety testing in terms of thermal endurance testing include capacity retention. We measure how much charge the battery holds after cycling in extreme temps. If capacity drops too far, the battery is unreliable. Charge and discharge efficiency is next. Thermal stress impacts lithium-ion movement. Colder temps slow it down. Hotter temps decrease internal resistance. Electrochemical stability. At high heat, you risk electrolyte decomposition. In cold, lithium plating becomes a risk, which can cause dendrites, leading to internal shortening. At low temperatures, the organic solvents in the electrolyte become significantly more viscous. Viscosity increases by an order of magnitude or more, slowing down the movement of lithium ions through the solution. This leads to poor ionic conductivity, which means reduced cell power output, slower charge acceptance, increased internal resistance, and the possibility of lithium plating. Imagine stirring syrup straight out of the fridge. Now imagine lithium ions trying to flow through that thick syrup. During charging at low temperatures, especially with high currents, lithium ions cannot intercalate into the graphite anode quickly enough. Instead, they begin depositing as metallic lithium on the anode surface. This is known as lithium plating. Plating lithium is electrochemically inactive, which reduces capacity. Dendrite in form, which means it risks internal short circuits and overheating that can lead to thermal runaway. And it is irreversible. Once it forms, permanent battery degradation occurs. Next up, let's look at high temperature soak conditions. As temperature increases, the electrolyte becomes less viscous, almost like water at extreme temperatures. This improves ion mobility, reducing internal resistance and enabling faster charging and discharging. However, this improvement comes with thermal trade-offs, including chemical stability risks. The same high temperatures can accelerate electrolyte decomposition, such as solvent breakdown and SEI, or solid electrolyte interface layer degradation. It also generates CO2 and CO and hydrofluoric gases. These chemical stability risks can lead to swelling of pouch cells, increased internal pressure, and gas venting or even case rupture. You also have accelerated degradation. The anode and cathode materials suffer from accelerated side reactions at high temps. Metal dissolution from the cathode especially can migrate and destabilize the SEI. BMS protections must trigger thermal throttling or current derating during operation. Now let's go ahead and add water to the equation, specifically high humidity environments like tropical climates, monsoon zones, and coastal regions. During humidity testing, we expose the battery system to prolonged condensation and moisture exposure, especially during temperature cycling. Humidity tests often range from 10 degrees Celsius to 60 degrees Celsius temperature with a relative humidity of 90 to 95%. Dew-lap overlap is often employed as well to induce condensation inside sealed or semi-sealed enclosures. Failure risks that we look for during humidity testing include corrosion of bus bars, terminals, or welds, moisture ingress into vented housings, breakdown of conformal coatings or potting, and risk of high voltage shorting. Humidity can turn a minor seal imperfection into a catastrophic short circuit event if moisture bridges high voltage paths. On the topic of condensation in the air, let's talk about salt fog or salt spray testing. Salt fog and salt spray testing simulates highly corrosive marine and winter road salt conditions by exposing EV battery packs to fine mist of salt fog or spray solution. This accelerated corrosion test helps engineers verify battery enclosures and connectors resist corrosion, preventing dangerous electrical faults or failures in real-world conditions. Corrosion caused by salt and moisture can compromise battery integrity, potentially leading to electrical shorts, reduced battery life, or even safety hazards like thermal runaway. Specific failures due to corrosion include connector degradation, compromised sealing of battery enclosures, damaged electronics, and weakened structural components. By performing salt fog testing, manufacturers ensure battery packs are robust, safe, and reliable even in harsh coastal or winter environments. During salt fog testing, battery packs are placed in specialized chambers where they are exposed continuously to salt mist for several days or weeks, dependent on standards like UL 2580 or SAE J2464. Afterwards, the packs are carefully inspected for corrosion or performance issues, verifying compliance with safety regulations. An often overlooked yet mission critical area in EV battery validation is the coolant system. This is where we test for thermal instability, not from the cells themselves, but from the failure or degradation of the battery's thermal management system. Coolant system thermal instability testing evaluates the battery's coolant system response under conditions of overheating due to loss of flow, blocked or airlocked coolant lines, pump failure, cavitation, or under pressure events, and rapid changes in thermal load, such as with fast charging or hill climb under load. Key test conditions include that the coolant system operates at varying flow rates and pressures. Testing includes inducing flow interruptions, valve malfunctions, or partial blockages. It also includes testing under maximum cell heating scenarios, such as C rates of 2C to 3C charge or discharge rates as an arbitrary example. Ambient and internal temperatures are monitored at multiple points during the test. Parameters that are monitored include coolant loop pressure response, which includes PSI versus flow stability, cell to coolant delta T or temperature gradient efficiency, thermal uniformity across the pack, BMS temperature sensor accuracy and response delay, and activation of emergency thermal countermeasures such as throttling or limp mode. Why does this matter? A coolant system's failure doesn't cause immediate thermal runaway, but it sets the stage. As internal pack temperature climbs, passive safety margins erode quickly. There have been cases where a blocked coolant channel can cause cell-to-cell variation of over 20 degrees C, enough to trigger premature aging and even lead to thermal events under load. Failure modes include pump cavitation and vapor lock, radiator airflow restriction, reservoir pressure regulator failures, non-uniform thermal spread leading to localized hotspots. Let's now dive into mechanical durability and safety tests. The first is vibration testing. On the road, batteries aren't static. They shake, rattle, and roll. So we simulate vibration from every possible terrain. Testing types include sine sweeps, random vibration, and mixed mode to mimic the layered vibrations a vehicle may see at high speeds over variable terrain. The objectives include that it ensures harnesses don't fatigue, prevent connector loosening, and validate the pack structure and mechanical fixations inside the pack. Next up is mechanical shock testing. Now let's talk impact. What happens if an EV crashes, or if a battery gets dropped during transport? Mechanical safety shock testing simulates things such as vehicle crashes, speed bumps at high velocity, and shipping mishandling. Shock waveforms include half sine, which are general purpose and mimic common mechanical shock environments, trapezoidal, which are longer duration impacts, and sawtooth, which are steep front edge simulating sudden energy delivery. We monitor how energy is transmitted through the battery pack, looking at peak Gs, response, and structural cohesion. A specific type of shock testing for drop events is drop testing. Drop testing simulates real-world handling abuse scenarios, such as drops during manufacturing, assembly, transportation, and maintenance. These are uncontrolled events. Battery modules or full packs may be dropped during shipping by a technician or even during installation. You'd be surprised how often batteries are damaged before they even get powered up. The test parameters for drop testing often include a test at a height of 1 meters to 2 meters depending on the application and standard followed. Orientations typically tested include flat face, corner impact, and edge drop. Surfaces used for drop testing include steel plate and concrete, with concrete being the common form of drop surface used for battery pack drop testing. What do we look for while performing drop testing? We look for structural damage to things like enclosure welds, module frames, internal compression structures, and connector and bus bar integrity. We also look for post-drop leakage of electrolyte or coolant, insulation breakdown, electrical functionality after drop. We recheck voltages, impedance, and insulation resistance. And also post-drop charge and discharge capability by performing a standard charge-discharge cycle, which many safety standards require. Failure modes include microfractures in cell casings, coolant fittings, cracks, or hose ejection, tab weld displacement on cells, deformation of mounting points that attach the battery to the vehicle chassis, and battery management system connector damage or high voltage path shorts. So what is crash testing all about? A crash test evaluates the structural integrity of EV battery packs under extreme mechanical stress. During this test, battery packs or modules are compressed using specialized equipment until specific load or deformation criteria are met, ensuring they can withstand real-world impacts. Standardized test parameters for crash tests typically include applying a defined force, such as 90 to 105 kilonewtons, or compressing the battery to a specific deformation, for example 50% of its original size. Testing should follow standards to ensure consistency and reliability in testing. Potential failure modes for crash testing include structural cracking, internal short circuits, electrolyte leakage, thermal runaway, or even fire. After the test, the battery packs are examined closely to identify these issues and ensure robust protective designs are in place. Next, we will look at electrical stress scenarios and charging system abuse tests. The first is external short circuit testing. What happens if someone damages the wiring or a connector corrodes? We simulate external short circuits to find out. The test setup for external short circuit testing includes terminal-to-terminal low resistance path. Typically, test setups are designed to have a short circuit resistance of less than 5 milliohms, lasting several seconds. They are monitored for thermal rise, venting, and fire events. Measured responses include peak current, often greater than 1,000 amps, activation of safety systems such as fuses, relays, and BMS cutoffs, and containment of thermal runaway in the event of a thermal runaway event. We use high-speed thermal imaging to capture the exact moment a cell heats up. That internal infrared signature is critical to understanding failure dynamics. Let's go ahead and look at charging system abuse tests. The first being overcharge testing, which pushes cells above their design voltage, which is typically between 4.1 and 4.2 volts depending on the cell chemistry. Risks of overcharging include lithium plating, internal shorts, gas formation, and even swelling. The next type of test is deep discharge testing, which simulates leaving an EV car parked with heavy parasitic draw. Risks include reversible versus irreversible capacity loss and BMS lockout. Outcomes of these tests include activation of cutoff circuits, monitoring for permanent damage, and checking BMS logic under stress. Let's look at passive propagation resistance, or PPR testing. Here's a test that separates well-engineered packs from the rest. If a single cell goes into thermal runaway, can the rest of the pack survive and contain the thermal event? With the amount of energy contained in such a small package, thermal runaway can happen. The key is to limit or even prevent thermal runaway propagation, which means the spread of heat and fire to neighboring cells within a battery pack when a single cell goes into thermal runaway. This is critical, as propagation of thermal runaway across cells can result in a full pack fire and ultimately a full vehicle fire. If a full vehicle fire happens rapidly after a single cell goes into thermal runaway, the ending results can be catastrophic and even fatal. This is why there are requirements, including GTR 20, provides requirements for a 5-minute warning to the driver and passengers to give them time to escape the vehicle. Thermal runaway containment and prevention is critical in the world of EV batteries. One spark, one hot cell, and if protection fails, you've got a runaway chain reaction. There are multiple methods that are used for executing a PPR test, including using nichrome wire wrapped around an individual cell, nail penetration, and even conductive heating. Depending on the requirements of a particular battery pack, the requirement could be single cell fault tolerance, which means if one cell goes into thermal runaway, all of the other neighboring cells cannot go into thermal runaway as well. Another requirement that you may see is that there cannot be any flame egress. So this means that the flame or the thermal propagation can spread to multiple cells as long as it doesn't end in a full pack burn down. Common causes of single cell thermal runaway in lithium-ion batteries include internal short circuits, which can occur from manufacturing defects, separator failure or damage, and foreign contaminants inside the cell. Mechanical abuse, including crushing or puncturing the cell. Excessive vibration or impact. Cell deformation, causing internal short circuits. And electrical abuse, including overcharging the cell, over-discharging the cell, or excessive current draw or charging rate. Thermal abuse can also result in single-cell thermal runaway, including exposure to high external temperatures, poor thermal management in battery design, internal overheating due to excessive charge and discharge currents. Electrolyte decomposition can also cause single-cell thermal runaway, including with chemical breakdowns due to excessive temperatures or voltages, and gas buildup from decomposition products. Cell aging and degradation can also cause single-cell thermal runaway, as dendrite formation over repeated charge-discharge cycles can occur. Also, separator deterioration over time can occur. Other manufacturing quality issues that can happen with the cell supplier include poor electrode coating or cell assembly, and inadequate electrolyte filling or sealing issues. Obviously, the most critical thing is to ensure that you are sourcing cells from a reputable cell supplier. But there are things you can do as a battery pack OEM or supplier to prevent and mitigate thermal runaway issues. Mechanisms that are implemented to protect against thermal runaway include thermal insulation, which could be high-temp ceramics, composites, foams, and gels, which are often employed in battery designs. Incorporating active cooling systems, using heat-dissipating materials and structures within battery modules, and ensuring consistent temperature monitoring and management. Also, it is critical to have a robust battery management system that includes accurate voltage, current, and temperature monitoring for as many cells as possible within your pack. And implement protective functions like cell balancing, overcharge prevention, and thermal shutoff. You should also have early detection and isolation for problematic cells. Another is mechanical protection. Robust cell packaging and cushioning to minimize mechanical damage, and reinforced battery enclosure designs to withstand impacts or crush forces. You should also implement electrical protections, including incorporating reliable fusing or circuit interrupters to prevent overcurrent. You should also use charge and discharge limiters to avoid electrical abuse conditions. Another critical aspect is cell spacing in your pack or module design, including physically separating cells or incorporating thermal barriers to prevent heat propagation between cells. And design modules to isolate and contain any single cell thermal event. In the field, it's critical to have regular inspections and maintenance, perform periodic checks of battery condition, capacity, internal resistance, and overall cell health, and remove or replace cells or modules showing early signs of degradation. Before you even put a cell into a module or a pack, a critical step you can add is to include electrochemical impedance spectroscopy, or EIS, for quality control. This helps with early detection of cell defects. By utilizing EIS, you can measure internal impedance characteristics, identifying subtle defects before cell integration into packs. You can also monitor cell degradation and track impedance changes over the battery lifecycle, detecting early signs of agent or dendrite growth when performing cell-level testing. You can also screen cells during production and implement EIS as part of the cell manufacturing quality checks, ensuring consistent cell quality and preventing defective cells from entering battery packs. Integrating EIS into the battery production and monitoring processes provides proactive detection of issues, significantly reducing the risk of single-cell thermal runaway. On the topic of fire, let's talk about external fire testing. External fire testing simulates real-world fire exposure from sources external to the battery pack. This test is used to determine how long the battery can resist thermal propagation and runaway, whether the pack undergoes violent rupture, thermal runaway, or cell venting, and the effectiveness of passive fire containment design of the battery pack. Implementation of the flame depends on the standard. However, a lot of standards include fuel fire, which is when a battery is placed over a pool fire, commonly gasoline or propane, for 70 seconds to 10 minutes, depending on pack size and standard. Typically, the flame exposure occurs horizontally or directly below the battery pack, but sometimes at an angle for corner exposure tests, depending on your requirements. Time to first cell venting. Measurements include time to first cell venting, time to thermal runaway if it does occur, magnitude of explosion or flare, structural containment behavior, flame penetration into the enclosure, and post-test pack behavior. Did the safety vents function as intended, for example? Failure modes for external fire include rapid thermal propagation due to heating of metal casings, gas expansion and gas rupture, gas expansion and case rupture, or even explosion, failure of burst discs or flame arresters, and burn through of aluminum housings at sustained temperatures. Remember, lithium-ion packs contain flammable electrolyte, pressurized gases, and hundreds or even thousands of individual cells. If the pack ignites violently, it can escalate into a vehicle fire exponentially. Design countermeasures for external fire include flame-resistant enclosures, which is a trade-off of requirements and costs, and balancing between using either aluminum, steel, or composite for your flame-resistant enclosure. You also need to consider pressure relief vents and rupture panels to relieve any pressure buildup caused by the venting of cells. You can also consider intumescent coatings or fire retardant barriers between cells, and thermal insulation zones that separate high-energy sections of the battery pack. When it comes to PPR testing and external fire testing, it's not about saving the pack, it's about saving lives. Lastly, let's go ahead and look at Ingress protection tests, starting with IP67 immersion testing. IP67 evaluates the watertight integrity of EV battery enclosures under short-term submersion. In automotive, the standard usually considered is ISO 20653. IP67 means that this battery pack must survive full submersion in 1 meter of water for 30 minutes with no leakage, no electrical faults, and no moisture intrusion into sensitive areas. When you see a term like IP67, the IP stands for ingress protection. The 6 stands for fully dust tight, no dust ingress. And 7 stands for immersion protection up to 1 meter depth at 30 minutes. This test is often one of the final validations in EV battery development and is mandatory for road-going water-exposed vehicles, including off-road, heavy-duty, and passenger EVs. The test setup includes charging the battery to 100% state of charge, and all ports, connectors, and pressure relief vents are sealed per production specs. The battery is immersed vertically or horizontally depending on your requirements in a tank at 1 meter water depth. It is monitored during and after for bubble formation, internal pressure changes, post-test insulation resistance, and post-test functional testing. The criteria for immersion testing includes no water ingress inside the enclosure, no drop in insulation resistance below safe thresholds, no corrosion or electrical leakage, and the battery must pass a full charge-discharge cycle after immersion. This criteria will vary depending on the standard that you follow and your particular requirements for your battery system. Risks of water ingress include short circuits due to moisture bridging, corrosion of high voltage bus bars or terminal studs, sensor malfunctions, especially temperature and pressure sensors, and electrolyte contamination or thermal event initiation in long-term storage. What makes this difficult? Well, battery enclosures often have vented membranes for pressure equalization, which must block water while allowing gas out. Coolant and high voltage connectors must remain sealed under both pressure and vibration in the field. And pressure differentials caused during thermal cycling or altitude changes can stress the seals. Even one drop of water in the wrong place can corrode a connector, destroy a BMS input, or trigger a service fault 6 months down the road or more. The next test is IP69K, which is high pressure spray testing. If IP67 simulates a calm flood, IP69K is a power washer to the face. It is the most extreme water ingress test most EV batteries will ever experience. The objective is to validate that the battery enclosure and all interfaces withstand high pressure, high temperature water jets directed from multiple angles without allowing any water intrusion into critical electrical or control systems. This is especially important for fleet EVs, construction or off-road vehicles, delivery vans exposed to daily wash runs, and military and tactical EV platforms. But let's be honest, a lot of us with our passenger vehicles also use a pressure washer to spray down our vehicle. And touchless car wash facilities also employ high pressure spraying systems to wash your car. The 9K and IP69K means protection against high pressure, high temperature water spray. Test conditions include water pressure at 80 to 100 bar or 1200 to 1450 psi, water temperatures at 80 degrees C, a flow rate of 14 to 16 liters per minute. Distance from nozzle is typically 10 to 15 centimeters, and spray angles include 0 degrees, 30 degrees, 60 degrees, and 90 degrees. Spray durations are often 30 seconds per angle, often with the device rotating on a turntable. This test is often repeated multiple cycles to simulate repeated washdowns or splash exposures. Results measured include ingress detection using humidity sensors or desiccant patches, post-test insulation resistance checks, functional tests of BMS, pressure sensors, and any external mounted components, connector seal integrity verification. Real-world risks of IP69K failures include water force past gaskets at high velocity, especially at connector pins or vent ports, hot water degrading polymer seals or adhesives, jet erosion of pressure relief membranes, false BMS triggers due to shorted signal lines or sensor anomalies, and it could also lead to thermal runaway. It's one thing to keep water out of a static enclosure. It's another to do it while the vehicle is getting pressure washed daily or hit by road blasts at 70 miles per hour. Some of the design challenges include connector interfaces, which need dual lip or triple lip sealing designs. Vent membranes must balance pressure equalization with splash resistance and often employ some kind of a splash or spray guard to protect the membrane. Mounting fasteners must be designed to avoid capillary leakage paths, and thermal expansion of materials must not compromise long-term seal performance. The last ingress test is IP6K dust testing. Water isn't the only thing that tries to get into EV battery packs. In fact, dust is even more insidious. It's fine, abrasive, electrostatically charged, and if your pack isn't sealed right, it will find every flaw. Dust testing simulates real-world dust exposure to validate that the battery pack is completely sealed against fine particulate ingress that could short electrical systems, damage BMS sensors, contaminate venting systems, degrade connectors and seals over time. The criteria for 6K is no ingress of dust, and it must be completely sealed. This test is often required for automotive-grade electronics exposed to harsh environments, including battery packs. The test setup includes that the battery enclosure is placed inside a dust chamber. The chamber is filled with a fine standardized dust, such as talcum powder or Arizona road dust. A vacuum can be applied to the pack, which is typically required for the 6K rating, and the internal housing pressure is brought down to negative 20 millibar to simulate pressure differentials during operation or altitude change. Airflow recirculation stirs dust continuously, and the test duration is typically 6 to 8 hours depending on whether you're following an ISO, UN, or IEC standard. Post-test evaluation includes disassembly and inspection of the battery pack, an inspection of connectors, seal edges, membrane vents, BMS housings, wire penetrations, and so forth. Visual and microscopic inspections are also performed to find any internal dust, and post-test insulation resistance checks are performed. Real-world risks of dust ingress include high-voltage arcing from conductive dust particles, corrosion and signal degradation at sensor and connector interfaces, seal erosion from long-term abrasive action, and false BMS triggers due to contaminated sensors such as pressure and humidity sensors. Dust doesn't cause an immediate failure, but it can cause eventual failure, and that's why this test matters. Design considerations include proper IP-rated grommets and cable glands, multi-stage labyrinth seals to deter particle entry, pressurized equalizing membranes that block particles but allow gas exchange, and hydrophobic and oleophobic coatings for exposed surfaces. These aren't just lab exercises. Every one of these tests is part of a story of resilience, innovation, and accountability. Next time you plug in your EV to charge, remember this: that battery in your car has been dropped, shaken, frozen, overheated, shorted, and abused, all before you ever got behind the wheel. Every mile that you have driven is backed by thousands of hours of extreme testing. I hope you enjoyed this video, and if you did, don't forget to hit that like button and subscribe to my channel. Thank you for watching and have a great day.